Welcome to The Explainer. Today we're taking on something that, let's be real, usually leaves students staring completely blankly at their Cambridge IGCSE math papers. Set theory. Yeah, it looks like an intimidating jumble of symbols, but we're going to transform it into a logical, highly visual toolkit that absolutely guarantees exam mastery.
Think about it. Before we can actually solve those multi-layered puzzles examiners love to throw at us, we got to learn to decode the secret language of set theory. It kind of looks like alien hieroglyphs, right? But once you get the translation key, these symbols tell a really specific, clear story.
Okay, so here's our roadmap for today. We'll be decoding set language, visualizing with Venn diagrams, tackling intersections and unions, unlocking the power of subsets, and finally, mastering those dreaded three-set problems. Let's just jump right in.
All right, Section 1, Decoding Set Language. We have to start with the fundamental building blocks. What exactly is a set?
Simply put, a set is just a collection of items, numbers, shapes, letters, whatever, that follow a specific rule. We call the individual items inside elements. Now, mathematically, you'll know you're dealing with a set when you see curly brackets. They act like fences. When you see them, you know a set is being defined, either by giving you a precise rule or by literally listing out the elements directly inside them.
Now this right here is your ultimate translation key. It turns abstract symbols into plain English. See that curly, script-like E? That's the universal set, basically the big box that all our current numbers are pulled from. That circle with a slash, the empty set. It means exactly what it sounds like. Nothing's in there. And that little curved E symbol means an item is an element of a set. If it's got a slash through it, it's not an element. Pretty straightforward, right?
But here's the thing. Precision is absolutely everything in this language. If the rule defining a set says integers from 1 to 10, and on the exam you just write the word integers, well, you're going to lose critical marks. The rule has to perfectly match the list of elements, 1 through 10. Precision is your best friend here.
Moving on to Section 2, Visualizing with Venn diagrams. Once we've got the written code down, we can start translating it visually. These diagrams, introduced way back in 1880 by John Venn, are literally your best tool for spatial reasoning. They use a large rectangle to represent the universal set. Think of it as the universe for that specific problem. Every single element we care about lives inside it. Then, our specific sets are drawn as circles or ovals inside that rectangle, which beautifully maps out how different groups of data relate to each other.
The trick here is visualizing the extremes. When two circles sit entirely apart from each other and share absolutely nothing, we call them disjoint. On the flip side, if one circle completely swallows another up, meaning every single element of set Q is also found in set P, we call that a subset.
Okay, Section 3. Intersections, unions, and complements. Let's look at what happens in the messy middle ground when these circles actually interact. Meet the three heavy hitters of set theory. The intersection symbol, that upside-down U. Think of it as the word and. It's only looking for the exact overlaps. The union symbol, the regular U, acts like the word or, and it just scoops up absolutely everything in both sets. And the complement, that's the little apostrophe after a set letter, and it just means not. It wants everything in the universal rectangle except what's inside that specific circle.
Let's see how this actually works. Say we have a universal set of integers from 1 to 20. If one set is factors of 12 and the other is prime numbers, their intersection, the stuff they share, only gives us the overlapping numbers 2 and 3 in the middle ends. But their union, that scoops up every single number from both circles combined. It's the whole shebang.
Now, examiners love testing your spatial reasoning by making you shade specific regions. Take a look at this concept, shading the complement of P intersected with Q. This forces you to visualize what is strictly outside the P circle, but simultaneously inside the Q circle. If you break it down piece by piece, finding not P first, then seeing where it overlaps with Q, it turns a really complex instruction into a simple coloring exercise. And before we move to the next part, just a quick reminder to subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations.
All right, Section 4, the power of subsets. Let's master a specific relationship that's a classic, tricky one-mark question.
We looked at subsets visually a second ago, but the mathematical notation is a sideways U with a line under it. Now listen closely, don't get caught out by this examiner trap. Technically, a set is always considered a subset of itself.
And even weirder, the empty set is always regarded as a subset of any set. Just memorize those two facts, they come up all the time.
And this little formula right here, it's a total lifesaver. 2 to the power of n. If an exam asks for the total number of possible subsets for a given set, please don't try to write them all out. Just calculate 2 to the power of n, where n is the total number of elements inside the original set. So if you have a set with 4 elements, like the letters A, B, C, and D, you just apply the rule. 2 to the power of 4 gives you exactly 16 subsets. It automatically accounts for all the 1-element subsets, the 2-element ones, the 3-element ones, the original set itself, and the empty set. No guessing required.
All right, the final boss. Section 5, Mastering 3-Set Problems. It's time to break down those high-value complex word problems.
Before we tackle the big diagrams, we have to talk about this notation shift. When you see a lowercase n outside the bracketed set name, you're not dealing with lists of letters or numbers anymore. You're dealing with a total head count. It represents the quantity of items that go inside a region, not the actual items themselves. Exam problems are going to throw walls of text at you about students playing sports or taking different subjects, and your job is to organize that chaos. For example, if you know there are 30 students total, and 6 study neither physics nor chemistry, that immediately tells you the number 6 goes entirely outside the circles.
Now, look at a massive problem like a 6th form of 200 students studying mathematics, technology, and psychology. Getting this right is worth serious marks. You'll get data like 110 study mathematics and 35 study math and psychology, but you can't just drop a 35 right into the overlap. That's a trap. Filling this out correctly requires a very strict strategy.
And here is your golden rule, the inside-out strategy. You absolutely must always start at the innermost intersection, the exact center where all 3 overlap. Place that number first. Then, methodically work your way outward, subtracting that center number from the 2 subject overlaps so you don't double count anyone. Only at the very end do you figure out the students doing just 1 subject.
So, by keeping this master glossary of set notation clear in your head, you take these intimidating symbol clusters and turn them into simple, actionable steps. Whether it's the universal set, an intersection, or the empty set, you now know exactly what the examiner wants you to do.
You've got the toolkit to translate abstract set theory into plain English. But here's something to think about. If mastering visual logic makes set theory this easy, how could mapping out data visually change how you tackle probability or algebra? Draw those diagrams from the inside out, and you'll see the math matrix for what it really is. And one last time, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Drop a comment below with your biggest math challenge and keep questioning the code.